Good afternoon. This is Earth History class, and this is our video lesson for Chapter 8. Chapter 8 is not a long chapter, or rather there's not a ton of information in there that we need. So this might be a shorter video that will quickly upload to YouTube. I hope so, we'll see. Alright, so Chapter 8 is Precambrian, but it's going to be the first half of the Precambrian, what we refer to as the Archean. Alright. So up there in the top there in the orange marker, Precambrian, remember our abbreviations there, Precambrian is divided into two different parts. And as I look at this, to be fair, I could have switched the order on those and put the oldest one on the bottom and the youngest one on the top, but I didn't. We'll just go with it as we have it. So the earliest Precambrian, by the way, Precambrian goes from roughly 4.57 billion years, as in the beginning of our planet, all the way until 541 million years ago. Okay, so now we're going to divide that into two different parts. Okay, so the early part is the Archean. Okay, so that's from beginnings of our planet, 4.57 billion, to 2.5 billion years. At that point, we're still in the Precambrian, but we call it the Proterozoic. And the Proterozoic is going to run from 2.5 billion years to 541 million years. So why do we make a break here at 2.5 billion years ago? And the answer is we will see a change in the style of crustal evolution. In other words, we'll talk about it more in Chapter 9. Okay, so Chapter 8's Archean, Chapter 9 is Proterozoic. And why does the Proterozoic and Precambrian end at 541 million years ago? Because that's when we're going to go into the Cambrian. And we picked that time period because that's when we start to see the Cambrian explosion, meaning an explosion in the diversity of life forms on this planet. And of course, we won't get into Cambrian life until a later chapter. Alright, so the oldest known rock that is an actual rock is the Acasta gneiss, located in Canada. Maybe I've mentioned this before in some previous chapters. Gneiss, remember, is, and that is misspelled. I did a dyslexia there. That should be G-N-E-I-S-S. Gneiss is a high-grade metamorphic rock. So the Acasta gneiss is some of our oldest continental crustal material on the planet, 3.96 billion. Now in blue, we find evidence for continental material going back all the way to 4.1 billion, but that older evidence is in the form of detrital zircons. So zircons are minerals. Detrital means they have weathered and eroded out of their original rock. So and the Acasta gneiss is a granitic gneiss, meaning that the parent rock, original rock that formed, was granite. As we finally started to eventually have some, say, ocean, we formed some protocontinents, and then we had some ocean to continent subduction zones forming and giving us more felsic melt, leading to granite. And then that granite is so old it has been metamorphosed into granitic gneiss. Anyway, so the detrital zircons tell us that we probably had granite crust going back to at least 4.1 billion. We just don't have the rest of the rock. We only have those zircons that we find. And the radiometric age date on the zircons is 4.1 billion. Okay, so what we think of as Earth's atmosphere, as in the gases around us that we breathe and our surface water, came mostly from volcanic outgassing early in Earth's history. But the physicists would remind us that early Earth was bombarded with a lot of meteorite impacts, and perhaps even some comets back then might have smacked into us and brought the necessary elements to make water and our atmospheric gases. All right, moving on. Move these chairs around a little bit. Hopefully the lights aren't going to go out on us, but they might. All right, so the first crust on this planet most certainly had to be basalt. But we don't have any basalt in an ocean basin anyway, going back more than 180 million years. We don't have any really old basalt. Why? Because we would have formed basalt crust and then it just would have been smacking into other basalt crust and you would have had ocean to ocean subduction zones basically. And of course, as it does today with modern subduction zones on this planet, that's going to destroy your old oceanic crust. Okay, so eventually these ocean-to-ocean subduction zones would build island arcs. So an example of a modern island arc, there in parentheses, the Mariana Islands, which is where the Mariana Trench is, which is the deepest part of any ocean trench on this planet at 7 miles deep. Anyway, just to give you an example, something that you can kind of keep in your head is what would a tiny old island arc look like? Well, it would have looked very much like the Mariana Islands today. So when you get ocean-to-ocean subduction zones, okay, eventually you're going to lead to intermediate melt. So instead of melting and producing more basalt, you're going to start to produce diorite. So diorite is an intermediate rock. It has roughly half felsic and half mafic minerals, and now you're starting to form continental material. Okay, what's important about that is that continental material is basically it's light enough in its density that it's not going to subduct. Okay, so eventually you're going to build some larger island arcs. And then those island arcs, they're moving around the planet with plate tectonics, and they're going to smack into each other here and there. And they're going to combine and form proto-continents. So if you have a subducting oceanic slab, you know, making contact with a continent, say an ocean-to-continent subduction zone like we find today up in the Pacific Northwest off the northwest coast, if you have any island arcs on that oceanic slab, the island arcs do not subduct. First of all, they're just really too big, and then again, they're going to have some of that intermediate material. So island arcs will smack into each other, and they're not subducting and destroying the material. Instead, they're going to start to form proto-continents, as in small continents or very early continents. And of course, rock is going to be highly metamorphosed in these events. Now, eventually, you're going to get these, you know, proto-continents here and there, and then you'll have, you know, oceanic slabs making contact and subducting. So eventually, we're going to see ocean-to-continent subduction zones that form, and then we have the possibility of not just intermediate melt, although we can get intermediate melt here, but we'll start to see more felsic melt, like we might see in the case of Mount St. Helens, a very active and dangerous stratovolcano in the Pacific Northwest. Its magma type there is roughly halfway in between felsic and intermediate. Okay, moving on some more. All right, so our Precambrian continents are going to consist of, so these are our early continents, and we didn't have quite as much land mass back then, and our continents weren't quite as big as they are now. But your Precambrian continents are going to consist of the continental shield and the platform. So the continental shield is the oldest portion of a continent. So for North America, our shield is called the Canadian Shield, because it's pretty much all in Canada where you find this oldest part of North America that is exposed to the surface. Now, there's still old North America down here in parts of the United States, but it's covered with sediments, therefore we call that the platform. It's not the shield because it's not exposed. It's the platform. And all continents are going to have their continental shield and platforms, which are basically the oldest portions of those continents. In later chapters, we'll talk about island arcs, smacking up onto continents, and adding onto the continents. Okay, but the continental shield and platform are the oldest portions of any continent. In the PowerPoints for Chapter 8, we've got some good drawings, maps to show this. Hopefully we'll have 5 minutes in class someday to take a look at that. Okay, so how about the rocks of the Archean? They consist mostly of granitic gneiss complexes with some greenstone belts. Okay, so what is a granitic gneiss complex? Well, first of all, gneiss, remember, is a high-grade metamorphic rock. Granitic gneiss means that granite was the parent rock. So basically our cratons and the covered portion, the platforms, are basically, our modern cratons and platforms are consisting of these very old granitic gneiss complexes from the Archean. But you'll have some greenstone belts here and there. Okay, so how about those greenstone belts? Well, let's move on and take a look at a drawing of a greenstone belt. Drawing doesn't do it justice, but there's a really nice image of an old greenstone belt up in, say, Michigan or Wisconsin in the PowerPoint for this chapter, and in your textbook, I'm sure the image is there as well. So mostly these old rocks from the Archean are granitic gneiss. But here and there, we see these old features called greenstone belts. Greenstone belts are not forming anymore. They don't form on this planet anymore. But they did in the past, and we know because we find them that have still here, not eroded away. So they tend to have a synclinal structure, meaning it looks like a syncline, as opposed to an anticline. So, kind of depends on who you took for earth science. And unfortunately, because we are made to teach earth science and not physical geology at this school, I don't really have time to cover anticlines and synclines because I have to stop everything and do atmosphere and weather. Okay, that's not by my choice. I think we should teach physical geology, and then I would have time for anticlines and synclines. If people want to learn about the weather, they could take the weather and climate class. But I don't get to make these decisions. So, an anticline occurs when you take rocks and you fold them and they're doming upwards. A syncline, which we see on the board here, occurs when you take rocks and you fold them, as in you have some kind of convergent boundary and you're pressing on them from the sides. You fold them into something that is opening upwards. In other words, we might refer to this as holding water instead of dropping water. So the synclinal structure of these greenstone belts, it basically works like this. On the bottom, you're either going to have basalt that's been slightly metamorphosed, or you're going to have peridotite, which is our ultramafic melt. Okay, so ultramafic magma no longer erupts at Earth's surface. It did in the past. We know that because of these greenstone belts. It did in the past when Earth was younger and had more internal heat. And that other word there, and it looks like I've misspelled it, but I haven't, komatiite, is the extrusive variety of your ultramafic melt, the extrusive variety of peridotite. Your second layer up is basalt, and then your top layer, sedimentary rocks. Now the basalt in the greenstone belts is not just basalt. It has a greenish tinge to it, okay? It's called greenstone. And what is greenstone? It's basically slightly metamorphosed basalt. But again, the presence of that peridotite or komatiite lets you know that this was ultramafic melt erupting at our surface in the past. Now, in the textbook and perhaps in the PowerPoints, there's some discussion there on how the greenstone belts formed. You will not need to know that for your exam. I just want you to know what they are. Okay, so rocks from back in the Archean were basically granitic gneiss, a whole lot of granitic gneiss, metamorphosed granite, with some of these greenstone belts throughout. All right, moving on. Hoping the light doesn't go out. Okay, so something we've mentioned before this semester. Early in Earth's history, there was more radiogenic heat. Okay, so Earth is heated. We do have internal heat, but we are losing some heat with time. So we used to have more heat. Okay, and we know this because we find evidence of this ultramafic melt that erupted at Earth's surface in the past, producing this rock that is part of the greenstone belt. And of course, this material clearly was later folded. They're not flat lying, they are folded into synclines. And something else we probably mentioned early in the semester, we're pretty sure that the plates moved a little faster back when we had more radiogenic heat. All right, so In the Archean, we don't have much evidence of passive margins. Okay, so just to remind you, what is a passive margin? Well, we actually talked about it in class today. This is the week of February 22nd, and we were starting into, we're still in Chapter 3, plate tectonics, and starting to get to the plate boundaries. So a passive margin, just to jog your memory, is a coastline that is not, shoot, I knew that was going to happen. All right, so we're walking over to the door, all the way to the door, to make the light come back on. Boy, it's dark in this room. Okay. All right, back where we were. Okay, so again, what is a passive margin? It's a coastline that is not a plate boundary. Great example of a passive margin is the east coast of the United States. We have plenty of passive margins on our planet now. East coast of the U.S., east coast of South America, west coast of Africa, Western Europe coastal area. But here's a weird thing. We really didn't have these passive margins in the Archean. We basically had a whole lot of active margins, a lot of subduction zones going on. Now we're going to see passive margins start to appear in the Proterozoic, and we'll talk about that when we get to Chapter 9, which I will film next week. All right, moving on. So we're sure that there were several small cratons, as in protocontinents, several small cratons present during the Archean. And eventually, these small cratons from the Archean would come together to form Rodinia, or Rodinia, if you prefer the British pronunciation. And that'll happen in the Proterozoic. So we've already mentioned Rodinia previously in this semester. Remember that it was the supercontinent before Pangea, and it was smaller. We didn't have quite as much continental material at the time. So we think that by the end of the Archean, around 2.5 billion years ago, we probably had 30 to 40% of the present volume of continental crust. So it kind of makes sense. We didn't have the volume of continental crust we have today at the end of the Archean. Therefore, in Proterozoic time, when Rodinia forms, yeah, it was smaller. Not as much material as we had either in Pangea times or what our map looks like today. All right, so we are moving on to, I just moved a button. Which button did I move? Okay, it was the iris, so that's all right. Not the end of the world. Okay, our last bit of notes here in green. Let me get to a point where I think we don't have too much light glare. Okay, so very early Earth, very early, our atmosphere was likely hydrogen and helium. Okay, that's not material that we could breathe and live with today. Of course, we know things are better now. So slightly later on, it probably evolved to consist mostly ammonia and methane. Again, gases that we could not breathe today. So this would have given us a reducing atmosphere. Reducing, not oxidizing. Okay, so in your sedimentary rocks that were forming at that time, this could lead to a greenish color in those very old sedimentary rocks from that time, or the sediments that might be left behind now. Okay, so we did have oxygen in early Earth atmosphere at some point in the Archean, and it was a small amount. Like our current percentage of atmospheric oxygen, O2, is 21%. We think it was probably about 2% during the Archean, and this came mostly from photochemical dissociation. All right, so what did it take to produce the greater oxygen levels that we saw since the Archean and that we enjoy today? And that answer, of course, is photosynthesis. Now, photosynthesis actually began in the Archean, but it's really going to take off later on. Okay, so that bottom bullet there in green, I'm sure we have mentioned before, probably at least a couple times. So our oldest fossils that are undisputed fossils are stromatolites. And these are basically fossilized algal mats. And the stromatolites are cyanobacteria, blue-green algae. Okay, we're talking single-cell organisms here. And of course, these oldest stromatolites go back 3.5 billion years. Do we have stromatolites today? Yes, we do. We have some living in Sharks Bay, Australia. So stromatolites also are considered living fossils. Our last little snippet for Chapter 8. Okay, so life forms in the Archean, not particularly advanced, other than your stromatolites, you're very early. It was basically bacteria and archaea, and there are some fossil micrograph pictures of archaea in the PowerPoints and probably in the textbook as well. So bacteria and archaea were present in the Archean, and these things are prokaryotes. Okay, so they weren't all that advanced. I mean, they may have had some organelles, but they were lacking what we would consider to be a true nucleus. Now, if you remember from your biology class, the eukaryotes are the more advanced cells, and we're going to see them appear in the Proterozoic. So we'll talk about that in Chapter 9. Okay, that's it. That does it for Chapter 8.